Okay, so NMR, the primary tool of the organic chemist to figure out structure. So the first kind of NMR that you learned, who is familiar at least with Proton Nmr? Proton Nmr. Okay, so we're going to talk first about Proton Nmr, and we're going to do it from a very practical standpoint. I'm not going to talk about theory today. It's just going to be practice. How do you get information out of spectra, essentially? Carbon-13 NMR. Have you been exposed to carbon-13 NMR? Mm-hmm. Okay, good. So let's start with that, and then we'll move into these higher level experiments. So in a Proton NMR, there are primarily three pieces of information that we get when we're looking at a Proton NMR. What are those three pieces of information we get for any compound? What are the three things that we're looking at? And we're just going to start with a simple example. Ethyl acetate. What are the three characteristics of each signal that we're looking for? Integration is one. So integration tells you about what?
How many hydrogens are in that environment?
Yeah, how many hydrogens are in that environment? So we have integration. Okay, and what's another piece of information we get about every signal?
Shifts.
Yeah, chemical shifts. Right, so we get, chemical shift. And usually you call that delta if the unit is in parts per million, right? So the chemical shift is also unique for a particular group of protons. What's the other piece of information?
Multiplicity.
Multiplicity or scalar coupling, right? Coupling. Okay, so let's talk about each of those kind of separately. Just in general terms, what determines the chemical shift of a proton in general?
Shielding and deshielding.
Shielding and deshielding. There are other artifacts like diamagnetic anisotropy and things like that. But the chemical shift of a proton relates to where it is in a molecule, and that relates to if there are electron-neutron groups around or if there are pi clouds around that have circulating electrons, right? So the chemical shift of a proton group is characteristic of a position in a molecule, and you can look those things up on tables, right? So that table in front of you has a bunch of sort of common situations for a proton to be in. And one thing that you would do, and you're about to do it, is you would look at a proton group and you would say, what's the best analogy in the table for that proton group? And that would be your estimate of its chemical shift, right? You could estimate it. And in fact, that's what the tool we're going to practice is right now. We're going to practice estimating what spectra will look like, and then you'll work on interpreting later. Okay, so that's chemical shift. Coupling. What's coupling all about? What does coupling inform you about?
Neighbors.
Neighbors, right. So, and what kind of neighbors have the most profound coupling? Or what kind of neighbors will couple? How do you know whether to expect coupling?
Neighboring protons.
What's that?
Neighboring protons.
Neighboring protons. Proton groups, exactly. I like that better. So what you need to know is how many proton groups are next to a particular proton group, right? If you're talking about one proton in its own group, you're talking about how many neighboring groups are there. Yutan, would you mind closing the door? I think the background music might be just a little too much for the video. So that's scalar coupling, right? That's coupling. And let's just do a quick example. So this methyl group, right here, there are protons there. How would we determine what the coupling pattern would be or the splitting would be?
It has two buddies.
If you look next door, there's a proton group here that has two protons in it. Mm-hmm. And so we would expect that signal to look like a triplet. Yeah, so it splits kind of n plus 1, right? It splits one more than is in the neighboring group. Okay, that's the most simple kind of coupling. Okay? And then integration. How do we learn about integration? Like where on the spectrum is an integration, and what does it tell us again?
Area under a peak.
It's the area under that particular peak for a particular group. Okay, so we've been all just like saying proton group, proton group, proton group. How do you know that any two protons are in the same group or whether they're in different groups? What is the test that you apply to figure out whether two protons are in the same group or another? Let me give you an example. This carbon has two protons on it. if I want to argue, which we all already did, we already argued that that's one group of 2 protons. If I want to argue they're in the same group, what property must those protons have? In fact, there are 2 properties we can use to prove chemical equivalence. What are the 2 tests that we apply? Go ahead.
Symmetry.
Yeah, what kind of symmetry?
Plane.
Yeah, if you can pass an internal mirror plane through the whole molecule and one proton reflects on the other, then you've related those 2 and they're chemically equivalent. So here I've built ethyl acetate and I'll arrange it like it is on the board. And what you can see is there's a particular conformation and you're allowed to rotate bonds to see it, right? You can rotate bonds to make the thing symmetrical. And then if you imagine you can pass a mirror plane down, these 2 protons you can prove are identical because everything on both sides of that internal mirror plane are the same, right? If any element of the molecule is different on one side or the other, then you've broken the symmetry and they're no longer in the same group. Those all of a sudden become 2 groups, right? And they would couple with one another. Yeah? So that's one test. What's the other test that we can use to prove chemical equivalence? Hannah?
Bond rotation?
Rotation, right. And the rotation test is a little bit, maybe a little bit more confusing. The way I always like to think about it is if someone is showing the molecule to you and you have them take a look at it, a mental snapshot, and you have them close their eyes, Hannah, and you do a rotation and they open their eyes, and there's no way they can tell if you did anything or not, then you've proven that the groups you just exchanged are equivalent, chemically equivalent. So I could do that as many times as I want, and she would never know if I were actually doing a rotation or not when she closed her eyes. That proves by rotation that those are the same. If she could tell that I made a rotation, then they're not chemically equivalent by rotation. You could look for an internal mirror plane, right? But they're not chemically equivalent by rotation. So if you can prove any 2 protons are equivalent by one of those 2 tests, they're in the same group, right? So on a molecule like ethyl acetate, it's very obvious. How many proton groups would we expect? How many proton groups do we expect to see? 3. Yeah, we expect to see 1 here, 1 there, and 1 there. So the first thing I want you to do is I want you to work with your buddy or work on your own. I want you to predict the spectrum. And what I mean is predict these 3 properties for all of the proton groups in ethyl acetate. And you can use your tables. I have some blank paper here somewhere that you can use if you want to just work on a piece of paper. Ready to go? Okay. So we're back. Now let's actually do this together. So let's do them in order. Chemical shift, coupling, and integration. Chemical shift estimation for this.
2 protons.
2. Yeah, 2-ish. Yeah, a little more than 2. So delta of 2. And we found that on the table because that's a proton next to a carbonyl, right? A proton on a carbon next to a carbonyl. So delta of 2. Coupling. What multiplicity would we expect to see for that? Singlet, right? Singlet. And then integration. 3. Yeah, 3 hydrogens. Okay. The next proton group is here. What do you think? Chemical shift?
4.
I hear 1.7 and I hear 4. What's the best analogy? What's the most electronegative thing around? What's going to have the biggest influence? That oxygen. So look on your table for a proton on a carbon that's next to an oxygen. There should be 2 different variations. Like, you can have the tables, and that piece of paper is yours too, that blank piece right there.
Oh, and also smile for the camera.
Okay? All right. So what do you think? What's a good estimation?
4.
4, okay. And then the coupling? Okay, a quartet. And how did you do that reasoning?
3 buddies.
3 neighbors vicinal, right? And there's only 1 group, right? 1 group neighboring, and it's vicinal, and it has 3 members, so we would expect a simple quartet. Yes? Everyone comfortable with that? Integration?
2.
2 hydrogens. This group? Okay, so a delta of 0.8. Splitting?
Triplet.
Triplet. Integration? 3 hydrogens. All right, so I'm going to hand out data. Just look at the first page for now, and you can see how we did.
Oh, yeah.
Okay, how did we do?
Well.
We did very well with our interpretation, right? Okay, let's shift gears and let's do carbon. Make carbon predictions for this molecule. Carbons, in a carbon NMR, what's the only prediction we typically make?
Shift.
Just chemical shift. We don't typically look for, the way we run them decoupled, so the integration won't make any sense. And the multiplicities will all be 1. So for the carbon NMR, I'm going to erase these predictions, and then I want you to make predictions. Just leave your information packet closed and try to predict. Okay, so let's make predictions. How many different carbon groups do you expect to see in this molecule? 4, right? There are 4 carbons. There's no symmetry. An interesting thing you can often see in a carbon NMR is if there's symmetry, right? If there are 5 carbons but 2 that are symmetrical, you have 1 less signal than you would expect to see, right? So carbon NMR tells you about the symmetry of the molecule. Here there are no 2 carbons. We can relate by an internal mirror plane or by rotation, so they're all in their own unique chemical environment. So what's your best guess?
50.
50?
Oh.
What do you think? So look at your table.
She said 50.
Let's see. The table doesn't include one that is next to a carbonyl, right? It just doesn't have one like that in the table. So what would we guess? Is it going to be like around 20 or maybe 20 plus? Yeah, maybe 20. We'll just write 20 plus because that's the information we have, okay? We don't know for sure where it will be, but there it is. And then how about this one? Is there a good one in the table for? What do you think?
200.
So 200 is typical for aldehydes and ketones. This is an ester, which is a carboxylic acid derivative. So carboxylic acid's given there, so maybe 170, 180 might be a better guess because this is a carboxylic acid derivative. So I'll write 170 in there, 170, 180 for that one. And then what's the best analogy for this one, do you think? Ether or alcohol, and those would be around, yeah, about 70, right? Okay, and then this one, this methyl group,
5.
yeah, between 5 and 20, somewhere in that region. Okay, so go ahead and turn to the carbon, which is the next page that faces you when you open it up, and see, at 77 you'll see the solvent. No, the next page that faces you, this one. At 77 is the NMR solvent, so ignore the peaks at 77, and then have a look at what the actual chemical shifts are. So can we annotate the spectrum? Like, can you like write a letter next to each carbon and then? So where does this one actually appear?
14.
14, right? Okay, that one actually appears at 14. Where does this one actually appear?
60.
60. Okay, so these are the actual. I'll put them in parentheses. How about this one?
171.
171. And this one? 21. Pretty good. Okay, so we made pretty good estimates based on the tables. All right, is everyone comfortable with these ideas? Let's try a slightly more complicated example. Do all of those things to that one. All right, everyone. So we're gonna come together now, and we're gonna talk about this one. Let's label proton groups. How many different proton groups do we have? So how many groups are here?
1.
There's just one here, so I'll label it maybe group A. How many groups are here?
1.
So I'll label it B. How many groups are here?
1.
So that's group C, right there. How many groups are there?
1.
1, that's group D. How many groups are here?
2.
2, right? So we're going to have E, and we're going to have F here. Are there any others? Right, so that's it. So we expect to see 1, 2, 3, 4, 5, 6 proton groups. Yeah? And let's do that thing that we do with chemical shift, coupling, and integration. Chemical shift estimate. We look at our tables. What's the best estimate?
Like 5.5.
Yeah, 5.5 in that region. That would be reasonable. That's kind of an internal alkene. delta of 5.5. How about the coupling? What do you expect?
Just a doublet.
It has one group that's a vicinal neighbor, and there's only one proton in that group, so we would estimate a doublet for that. And then integration? One hydrogen. How about group B? Chemical shift? 5.2. Interesting. Why a lower chemical shift than the last one? Just curious.
It's farther from the carbon.
Yeah, that's interesting. Are inductive effects or resonance effects more powerful?
Resonance.
Resonance. So resonance actually has a lone pair on the nitrogen and puts a positive charge there. So actually a resonance effect is more important. So actually we should probably move it the other direction. Let's call it 6 because of resonance. Okay? So the alternate resonance form has a negative charge on the oxygen and a positive charge there. Okay? So 6 is our shift estimate. Then how about coupling? A doublet of doublets, right. It has 2 groups neighboring. They each have 1 proton. We would call that a doublet of doublets. And then integration? 1 hydrogen. Everyone comfortable with that assignment? Okay? Good. It seems like you have this stuff down. How about C? Chemical shift?
1.
I hear 1. Any counter arguments? What's the best analogy in the table? A proton on a carbon next to a double bond. Proton on a carbon next to a double bond is called allylic. Yeah, so like 1.8, 1.9. Parts per million would maybe be a better guess. Okay, and then multiplicity.
Doublet.
D.
Oh, no.
No. D from this direction. What from?
Triplet.
Oh, are those 1 group or 2?
Oh, no, 2.
2. So this would be a D from that one. How about from that one?
A D.
A D. So D.
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 Q.
Q.
Logic.
Yeah. All right. Is that all right? Is everyone okay with that?
What is a double?
It depends on the coupling constants. Okay. So how about group? Oh, integration.
1.
1C. Yeah, or 1 hydrogen. Okay. And how about group D? What do you think? Chemical shift?
1.
Around 1. That's a fine guess. And then multiplicity?
Doublet.
Just a doublet. And then integration?
3.
3. Okay. That seems to make sense. How about F? Chemical shift estimate?
3.
A proton on a carbon next to a carbonyl. What's the best one in your table? Yeah, it has that ketone one, so that's, yeah, like 2.3. Okay, so 2.3 with the chemical shift, and then how about the splitting? How many neighbors does it have, either vicinal or geminal to it?
It's a doublet of doublets.
It has E, which would make it a doublet geminally, and then it has C that would make it a doublet vicinally, right? And how many would that integrate to?
1.
1, yeah, that's 1 hydrogen. And then this one would be very similar, right, in all regards. It might have a slightly different chemical shift. Let's just call it 2 to make it different. Doublets, 1 hydrogen. Everyone comfortable with those assignments? Okay, let's do the carbon. How many carbon signals? 6? Yeah, there are 6 carbons, and no 2 can be related by any element of symmetry, right? So this is a ketone. So what's your estimate of chemical shift? 190? Sure. That's fine. How about this proton? I don't know what the best analogy is in your table. Your table is very limited for the carbon. What do think?
30.
30, all right. I'll buy it. That's not too bad for what you have for your table. And then this one. This is a tertiary carbon, right?
Mm-hmm.
Yeah, 45 would be a reasonable guess without a better table. This one,
20.
20. What do you think?
130.
130? Sure. How about this one?
And 60.
Again, this is going to be more deshielded probably, right, because of resonance, so maybe this is actually going to be,
100.
yeah, like 120. Okay? All right? Everyone see how to do those things.
Oh, I got it. That's on camera.
So ChemDraw is going to now predict those spectra for us, and we're going to see how well we did.
Okay. If you want the H.
Let's just do the proton NMR, and let's just do the chemical shifts. The multiplicities are hard to read off of the ChemDraw. Let's see how we did with chemical shift. Well, first of all, number of groups. Did we get the right number of groups? 1, 2, 3, 4, 5, 6.
This is saying 5 in. Or I need some values for 5.
No, it has 3 and 2. So that's 1, 2,
Oh,
3,
yeah.
4, 5, 6. So
Okay,
it got 6. And what did it predict for this one?
Is that A?
A.
6.07?
6. How about this one?
6.6?
6.6. Yeah, that's a little bit higher, right? Because of deshielding, right? About a half a unit higher. That's what we guessed, right? That's a reasonable guess. I'm not writing them down because these are just predictions as well, but, you know, maybe slightly better than our predictions. We'll see. How about
1.1.
1.1 for that one?
2.5.
2.5. So it's even a little higher than 1.8. That's because it's allylic, right? It's because it's allylic that it's a bit higher. And then D,
That's 1.1.
1.1, so we're really close on that one. How about these two? They're in different places.
One is 3.04 and the other is 2.79.
Okay, so we are a little on the low side, but these are right next to a carbonyl. Okay, so they're a little bit higher. All right, everyone comfortable with that? So we got the right number and the right ballpark. And if you understand how ChemDraw represents splitting, the splittings are right. You got the correct splittings. It shows you how many splittings are there. It doesn't label them the same way we do, but you can check using ChemDraw. Okay, so how about the carbon?
So starting from the top and going clockwise, 207.8,
207, not too bad.
47.4,
47.4, that's because it's next to a carbonyl. Okay,
26.8,
26.8 is further from the carbonyl.
19.2,
Very close.
164.9,
164 and then
134.
134. So 160 and 130 for that reason we talked about with the resonance. Everyone see what I'm talking about? Susanna?
What was the B and C carbon? There was the 30-hour estimate and 45-hour estimate. What were those ones?
These two?
No, 30 and 45 estimate.
These two.
47 and 27.
47 and 27. This one is different because we don't have a good analogy in our table for something that's next to a carbonyl. So we just threw out a guess, right? And actually, as it turns out, this one has a lower chemical shift because it's further away from that functional group. Okay, so I feel like you guys have a pretty decent handle on basic proton and carbon. Let's start talking about some of these higher order experiments like COSY and DET. So COSY, by the way, all of these experiments are listed on a page on the Moodle site, and I say exactly what information you get from each one. And so I'm just going to show you how to interpret that data. Okay, so a COSY, that's what I'm going to talk about next. COSY simply makes it very obvious which protons are coupling in a molecule. Okay, it makes it very obvious which protons are coupling. And so in this molecule, which two proton groups are coupling? If we label them, like we have proton group A, proton group B, and proton group C. Which proton groups are coupling?
B and C.
B and C. Okay, so we know that. This is a very simple molecule. The way COSYs are interpreted is this. They're actually a two-dimensional spectrum. And so we kind of expect to see a a triplet, and then a singlet, and then a quartet. Okay, so that's sort of our spectrum. And in a cozy, you have a proton on both axes. And down the middle, on the diagonal we call it, you see where these two intersect. So if you took a slice down the middle, a diagonal, you would actually see this spectrum. What a cozy does for us, though, is any two groups that are coupling, a peak that is off-axis appears. So we predict that B and C, these two are coupling one another. We kind of know that because, you know, this one's a triplet and that's a quartet, and it makes sense with the structure. But what you would see on a cozy is, you would see an off-axis peak where those two groups exist. And you would see it in both positions. You'd see it here and there. So any off-axis peak indicates that those two protons are coupling one another. This proton, as it turns out, this proton group C is not coupling to anything. So there's going to be no off-axis peaks for C. You with me? Everyone understand? So I've just made a rough prediction of the cozy. If you turn to the cozy now, which is exposed to you, that's the cozy of ethyl acetate. See how that works?
Mm.
Any off-axis peaks are a coupling. Make sense? So as the molecules get more complicated, you can see which two protons are coupling, right? If there are many, many proton groups and lots of coupling, you can tell exactly which two groups are coupling one another, right? So I picked a really simple example so you could really clearly see what the data show, right? Questions?
Is it online, the procedure, like how we do this?
How you do what?
Like how you do a
How you
cozy?
interpret a cozy?
No, how do you do it?
On the NMR?
Yeah. Is it just like a setting on there?
When you can't do it on this, well, you can do it on this little NMR, but I wouldn't recommend it. Use the one downstairs.
Okay, and
it's a button that says cozy.
And you
Instead
press-
of proton, you press cozy.
Okay.
And then the data just like comes out. And it's simple to work them up. Okay, like notice there are no integrations. All you do is put the projections on. And like you see how there's a projection of the 1D on this axis and 1D on that axis? You put those in there and get them all lined up so you can actually see exactly which groups are coupling with which. Okay? So again, ethyl acetate is a simple example. Okay? So, who has the Moodle page up? Okay, looks like Peyton already has it up. So, Peyton, will you read to us what a depth tells us? A depth, D-E-P.
It shows how many protons are attached to each carbon using combination with 13C NMR.
Yeah, so it shows us how many protons, it's an attached proton test. And what's the data like? How do we interpret it, Peyton?
If carbon has 3 or 1 protons attached, the peak will be positive. If carbon has 2 protons attached, the peak will be negative. And if a proton has 0 protons attached...
If a carbon has no protons.
Sorry. Oh, yeah. Yeah, that's a typo.
I made a mistake, sorry.
The signal will not be visible.
Right, so let's predict what the depth will look like for ethyl acetate. The carbon signal in a depth for this proton or for this carbon will be up or down or invisible. Has how many protons?
3.
3. If it has 3 protons, it should be
Positive.
positive. This one, how many protons attached?
2.
2, so it should be negative. This one, how many protons attached?
0.
0, so we should,
Not 0.
it wouldn't be visible in the depth. How about that one? Positive. Have a look at the depth and see if that bears out. But you see that, how the peaks are going in different directions depending on if they have an odd or even, and notice how the one that has no protons on it has no signal. Does everyone see what I'm talking about? So a depth allows you to figure out maybe which carbon is which. If you have many, many carbons, it's one way that it allows you to sort that out. Okay? So you can take a depth. You can run a depth very easily, very quickly. Okay, so we've talked about cozy, and we've talked about depth. Depth in HSQC and HMQC are very, very similar experiments, except the HMQC is a two-dimensional experiment, much like a cozy is. So let's talk about that. I don't have data for ethyl acetate for that one. I tried to run it, but it didn't. The experiment failed for some reason. So it's easy enough to understand, though. An HSQC or an HMQC is known as a heterocorrelation. And it's a heterocorrelation between a proton and a carbon. So, say for example, we're talking about ethyl acetate, we'll just predict what the HSQC would look like. So, on this axis is a proton spectrum on an HSQC, and on this axis is a carbon spectrum. Okay, so here we would have, like, that would be the carbonyl carbon, like at 170-ish, right? And then we're going to have one that's kind of the ether one, and then we're going to have two that are sort of the alkyl groups. Does everyone know what I'm talking about? So like the methyl and the methyl at the end of the ethyl. Okay, is everyone comfortable with this? So you have the spectrum right in front of you, right? Like I'm just doing it approximately. In an HSQC, cross peaks appear when a carbon is attached to a proton. So there are no protons attached to this carbon. That's the carbonyl carbon. So there are no cross peaks for this one. This one is the carbon that has the oxygen attached to it, right? That's the same carbon that has this quartet. So you would see a cross peak. So this carbon is attached to the proton that made that signal, right? See what I'm talking about? And so like this carbon is the one that's, say, next to the carbonyl. So that's the one that has the 3 protons that aren't coupling. You would expect to see a cross peak between those two. And similarly, this is the methyl group at the end of the ethyl, and you would expect to see a cross peak there. So this tells you even more than the det. It tells you exactly which proton group goes with which carbon. So you can identify exactly which carbon is which. Yeah? Everyone comfortable with that? Rachel?
Is it just another button that we press?
It's just another button.
Okay.
You hit HSQC.
Okay.
And then the data appears.
Okay.
After a period of time. Yeah? Okay? That's HSQC. Super useful. Super useful. Okay? HMBC. HMBC is another het core. HMBC is a powerful tool to determine connectivity. Peyton, you want to read to us what HMBC is supposed to show?
It shows 2, 3, or 4 more bond coupling between protons and carbon. The number of bonds can be set up in the experiment, but it is by default 3 or 4 bonds between the proton and the carbon.
Right. So I'm going to draw our ethyl acetate example again, and I'm just making like prediction spectra here. So HMBC is like HSQC, except instead of going just 1 bond away, it goes 3 or 4 bonds away. So let's look at ethyl acetate carefully, and I'll show you what that means. This is super useful for determining the structure of large molecules. So this proton in an HSQC has a cross peak with that carbon. That one's 1 bond away. You with me? In an HMBC, it's going to couple to a carbon that is 3 or maybe 4 bonds away. So that's 1, 2, 3, 4. That carbon and that proton will show a coupling. See what I'm talking about? That carbon and that proton will show a coupling. Yes?
Who's the third?
1 bond, 2 bond, 3 bond, 4. So it'll go through the oxygen.
Oh, goes through
It goes through the oxygen. So this
Okay,
is
that
1,
counts as
2,
bond.
3,
Alright.
4 bonds, and it's a het core, so it's coupling between a carbon and a proton. Yeah? Everyone comfortable with that? So you're going to see now cross peaks between this proton and that carbon peak. So let's show what that would look like. So that proton is this group, right? And that carbon is this group. So it's a different pattern than the HSQC because now it's 3 or 4 bonds away. Okay? Everyone comfortable with this? So we could predict all of the peaks we expect by looking 3 or 4 bonds away. So how about these protons? Which ones would you expect an HMBC? Which carbon or carbons would you expect to see an HMBC peak for that proton? 1, 2, not far enough. 1 bond, 2 bonds, 3 bonds, that carbon. 1 bond, 2 bonds, 1, 2, 3, 4, that carbon. So that proton, right, which is this set right here, might have 2 different cross peaks. One with the carbonyl peak, and one with this one. The one that's next to the carbonyl. Does everyone see what I'm talking about? So that's a 3 or a 4 bond coupling. So you can actually like look some distance away in the molecule from one proton. And you can actually set how many bonds away you want to look. Typically it's 3 or 4 bonds. All right, that's all I'm going to talk about today.